Guys, so one thing you might have been noticing from the first part of our notes from linear expansion was when expansion occurs, why would it always be in one direction? Or like, why would it be in one direction? So it isn't actually. So I not quite lying to you, but kind of. So as the particles gain more energy and move faster and spread out, the whole object is spreading out in each direction. When we are talking about linear expansion, however, the length is so much longer than the width that this is so negligible that we don't really have to take it into account because it's so much longer that uh, we're just going to be looking at direction, length change in one direction. But if we have something like a liquid or like a cube of metal, then there is no specific length. It's going to expand in all directions. Then it was three-dimensional, like the same. Okay, so it will expand in all directions. It's just when we're dealing with linear expansion, it's so much longer that we can ignore this small little bit of width expansion. Okay, so volume expansion is just taking our linear expansion and applying it to all directions. So increases in all three directions. So we can think of this just as being linear expansion in three. Now, volume expansion is going to have basically the exact same formula as our linear expansion. So our change in volume still depends on, well, what was our volume originally? What is the coefficient of volume expansion? And how much is the temperature changing? So how much hotter or colder is it getting? So same thing. I'm just going to pause this and write our variables in since they are the same, then I'll talk about them. So delta V, once again, change in volume. So remember, anytime I see that delta, it's just V2 minus V1. My V1 is my initial volume. My coefficient of volume expansion is my beta, so kind of a B with a little line down. And delta T is my change in temperature. Now, our units, so when we're dealing with volume, we are talking meters cubed. Remember, meter squared area, meters distance, meter cubed is a volume. Or it could be in liters. So either or. So our initial volume will either be in meter cubed or liters. Our coefficient of volume expansion, same thing as it was with linear expansion, per degree Celsius. So degree Celsius is the -1. And our change in temperature is still degrees Celsius. So we're going to do an example here. So our lecture example 3, if the coefficient of volume expansion is 38 times 10 to the -6 degrees Celsius -1 in a liquid that was originally 45 meters cubed and ended up being 45.1 meters cubed, what was the change in temperature? What was the final temperature if the original temperature was 12 degrees Celsius? Okay, so it's not, it's only raising or gaining in volume by 0.1 of a meter cubed. So not a whole lot, but still enough to cause havoc. Okay, so what was the final temperature if the original temperature was 12? So taking a look here, always doing our givens first. We're looking for final temperature. We have our coefficient of volume expansion. So it gives us our beta. We don't have to look it up in our chart. So 38 times 10 to the -6 degrees Celsius to -1. If I was unsure what this number was, if I was having problems just reading through and getting the information from this question, I could always look at the units. Anytime I have a degree Celsius to the -1, I know that's going to be a coefficient. Over here, anytime I have anything in meters squared, I know that's either going to be a length or a change in length. So we have something that was originally 45 meters cubed and ended up being 45.1 meters cubed. So here I have an initial volume and ended up being, so final volume. So I can calculate my change in volume by doing V2 minus V1. So my final volume is 45.1 meters cubed. My initial volume is 45.0 meters cubed. So my change in volume is just 0.1 meters cubed. Now, what was the change in temperature? And what was the final temperature? So looking for delta T, and then after that, so this is like an A, then looking for my final temperature, when my original temperature was 12 degrees Celsius. So T1 equals 12 degrees Celsius. Okay, so writing our formula, delta V equals V1 beta delta T. Now taking a look, hey, yo, wait, I have my delta V, I calculated that. I have my beta. I'm looking for delta T first, so finding my change in temperature first. What was my V1? I didn't write that down. Oh, right. My volume was initially 45 meters. So I just had that here. Don't forget, V1 is 45 meters cubed. Sorry, not meters. So I do have my V1. So solving for delta T, so it's multiplying, so divide by V1 and beta. What I do to one side, I must do to the other. So gone. I'm left with my delta T. So my change in temperature equals delta V over V1 beta. Substituting in, so delta V is 0.1 meters cubed divided by my initial volume, 45 meters cubed, and my beta, so 38 times 10 to the negative 6 degrees Celsius negative 1 equals. So this divided by this and then divided by that, or you can make sure you put this whole denominator in brackets, or you could figure out what the bottom is, then do the numerator divided by denominator, however you find it best. But you should still end up getting, as long as you're putting everything into your calculator correctly, 58.479, so on and so forth. This is a change in temperature, so degrees Celsius. If I was unsure of my units, I could always check meters cubed cancels out. I have a degree Celsius to the -1 on the denominator, which means it moves up to the numerator. So I do get units of degrees Celsius. So now we'll have to round this number. So looking at our original equation, once again, please don't use, I'm just gonna tell you, do not use constants for sig figs. So don't use constants. Once you get to higher physics classes, you will be using the constants for physical science 20. Don't worry about it. We're just going to ignore those. So multiplying, so 3 sig figs, 3 sig figs, 3 sig figs, we're going to round to 3. So 58.47, so that 4 is going to round up to a 5. So 58.5 degrees Celsius is my change in temperature. So that's my first answer. The sig figs would actually be a little bit different since there is a subtraction in here. Remember, the rules for addition and subtraction are a little bit different, but since we do end up multiplying, I'm just going to simplify it because I know you guys hate significant figures and say, okay, multiplying and or dividing, just look at your least amount of significant figures. Okay, so B, we need to find our final temperature. Now we can think through this and figure it out, or we can actually just use our formula. So if we were thinking through, if our change in temperature was 58.5 degrees Celsius, now taking a look, I went up in volume, which means that my temperature was raised, right? So that means I'm gaining 58.5 degrees Celsius. So if it was 12 degrees Celsius, then I just need to add 58.5 degrees to that and I'm good. The other way we could do that, if you weren't sure if you need to add or subtract and you weren't good at thinking it through, remember delta T just equals T2 minus T1. So solving for T2, it's going to be just delta T plus T1. And we know that our change in temperature, we calculated that, was 58.5. And our original temperature was 12.0 degrees Celsius, so 58.5 plus 12. So you can do it mathematically, or you can just think about what's actually happening in the question and show your calculation from there. So you will still have to show your work, the 58.5 plus 12, but you would not necessarily have to show the formula up here if you're just thinking it through. So 58.5 plus 12, you get 70.5 degrees Celsius. So T2 equals 70.5 degrees Celsius. And so since this is adding and subtracting, it's just to the least amount of, or sorry, the like highest decimal place. So one decimal, so 70.5, or lowest decimal place, sorry. Yes. So our two answers, 58.5 degrees Celsius and 70.5 degrees Celsius. Okay. So where we see volume expansion, overflow tanks, so in your car, so your radiator. If you put too much gas in, say it was like a cold morning, you put in your gas, you filled it right to the top, and then you didn't drive very far, you just let it sit, your gas might might expand. Instead of bursting your tank, we have an overflow tank. So that's nice and handy. Thank you, radiator. See volume expansion in thermometers. So as the temperature rises, the liquid in the thermometer will expand, so causing it to go up. As it cools, the thermometer's volume will go down. So the liquid will go down, it will contract. Right? So your assignment is page 362 and 363, these three questions, and 369, 370, these questions here. Okay,